In this video, we're going to review and talk about ionic compounds in more detail. By the end of the video, you should be able to determine which atoms form cations and which ones form anions, determine the charge of representative elements on the table, and construct chemical formulas for binary compounds, or compounds made of only two elements. So we review that ionic compounds have metals and nonmetals in them. And now we should know that the metal particles tend to form positively charged ions, or cations. The T in cation kind of looks like the positive sign, right? And a nonmetal particles form negatively charged anions. So anions, it sounds like anti, right? Or negative. And so together in salt, regular table salt or sodium chloride, the metal sodium is positive and the nonmetal chlorine is negative, and that's how they sum to form a neutral compound. Anything that can conduct electricity in the liquid phase were called electrolytes. And if you remember back to our bonding lab where we conduct electricity with a light bulb, we saw that water did not conduct electricity because it doesn't have the metal and nonmetal parts. In table salt, when it's solidified, it also didn't have the plus-minus charge. It was completely neutralized and had a rigid, tight structure, so it did not conduct electricity. But when we dissolved it in the water, all the positive cations separated from all the negative anions, and those charged particles were able to conduct or move electricity through the light bulb. And so that one did conduct because it was an aqueous phase. Ionic compounds' ratio of atoms are based upon the charge of each ion they form. So in an example of sodium chloride, the reason we only have one sodium and one chlorine is because sodium is a +1 ion all the time and chlorine's a -1 ion all the time, and to sum them you'll get a value of 0. In calcium chloride, calcium has a +2 charge, and each chlorine's -1. So you need to have 2 chlorines to balance the charge to 0. In general, group 1 metals tend to form +1 cations, and you can see that in the top right corner of everything's box. And that's why we saw sodium being a +1 ion. In group 2 elements, you're seeing that these form +2 charges, +2 in the top corner of each box. And that's why in barium chloride, barium is +2, so you'll need 2 chlorines to match the charge. Group 13 metals, notice we're missing the middle. We're doing just the big chart, the taller table parts. So in aluminum or something like boron or gallium, they're all +3 charges, and so if they're a +3 charge, they'll need 3 chlorines to balance their charge. We're going to skip group 14 because it is a little troublesome, and go to group 15. We'll do group 14 in the future. In group 15, we're now talking about nonmetals. Nonmetals have lots of charges, so we're going to look at just the top charge as the most common charge. So the most common charge for something like nitrogen or phosphorus is -3. That's why it only combines with other metals, and for example, with sodium, it would need 3 sodiums because we know sodium is +1. In group 16, they also have multiple charges. We're looking at the top charge as the most common one, and the most common charge is -2. So in that case, if it was reacting with something like sodium, this was a group 1 ion +1, you would need to have 2 sodiums, and so this would be inaccurate. It would have to be Na2O. And last, in group 17, the nonmetals are -1 charge and the top most common charge, and so that's why NaCl worked out as 1 of each, +1 -1. Group 18 elements, what you'll notice, do not form ions. They all say 0 on the top. That means they're unreactive or inert, and they can't form compounds. For some reason, they always say gaseous particles that don't react. So when we're writing our chemical formulas, we want to make sure the sum of the charges, or oxidation numbers as they're mentioned on the reference table, in a compound equals 0. Do not write 1s for their subscripts. So for example, the ones we keep seeing, sodium chloride, you only need 1 of each. So we know that it sums to 0, and we just write it once, NaCl. Let's do a couple more examples. If they wanted a formula between calcium and fluorine, notice that calcium is +2 and the fluorine's -1. So we would need 2 fluorines to balance the charge, or else it stays unbalanced. So we need to have fluorine happen again in order to do that. Instead of writing CaFF, we write CaF2. Fluorine happens twice. In another example, if we wanted to see how lithium and sulfur react, we check the top charges and say lithium happens +1 and sulfur always makes -2. And so if we left them like that, it would only be unbalanced. We would have an extra negative. So in that case, we need to add another lithium and another atom of lithium, or ion rather. And instead of writing LiLiS, we'll write Li2S. Also, we are seeing that when we write them, the charges usually are written plus, then minus, then plus again, because the 2 pluses shouldn't really be next to each other since positives repel. So we want to kind of catty corner the lithiums around the sulfur. If we're looking at barium and oxygen in example 3, barium is +2 and oxygen is -2, that actually works out quite nicely, that they'll balance out to 0 when you add them together. In that case, you don't need any extras, but we wouldn't write Ba1O1, we would write just BaO, one of each to balance the charge. At this point, you should be able to determine which atoms form cations and which are anions, determine the charge of the representative main group elements, and construct chemical formulas for binary compounds.